Good morning, everyone. It is a glorious moment to extend my warm wishes on behalf of the Wings of Aero. I want to convey my heartfelt gratitude to Ms. Louise RIOFRIO, scientist in Hawaii and NASA Johnson Space Center, for accepting the invitation and presiding over the seminar on a simple experiment for quantum mechanics and gravity. The webinar was organized and conducted by Wings of Aero for the science and engineering students to gain insight and information that would remain effective in their research and project. I will give the session to Miss Louise Riofrio. Ma'am, can we can start, ma'am?
Oh, good. Hello and aloha. I'm speaking to you from the Hawaiian Islands, and I'll quickly tell you a little bit about myself. I'm Louise. My background is in physics and astronomy. I've been working as a scientist at NASA Johnson Space Center in Houston, studying the moon, where I've been doing experiments with Apollo moon samples that no one has touched in 45 years. And I'm also using the moon to test theories of cosmology, as you'll see. Most recently, I've been here in the Hawaiian Islands, working on a project to place a telescope on a lunar lander. And recently, I've been named as a crew candidate for the Dear Moon mission to send a crew of humans around the moon in the year 2023. So I hope to make this exciting for you. This lecture is going to be divided into 3 parts. The first part is about, well, what I'm best known for, the speed of light. The second part will be about a way to possibly link quantum mechanics and gravity and a simple experiment you can do to demonstrate that. And the third part will be about the applications, which affect everything from cosmology to the size of the cells in your body to a possible way of understanding and maybe controlling gravity. Well, to begin, about 400 years ago, Galileo first pointed his telescope into the sky. Galileo was the first one to see the moons of Jupiter and the rings of Saturn. Galileo would invite other people to look into his telescope, but some learned minds of the day refused to look into Galileo's telescope. Why? Because it showed objects circling something other than the Earth. If you were to go to a lecture in the year 1609, they would tell you with every certainty that Earth is fixed at the center of the universe and that the sun and the planets travel around the Earth. Now, anyone observing the planets for any length of time will see that they sometimes appear to move backwards in their orbits. To explain this retrograde motion, scholars of the day imagined epicycles, circles within circles. The planets would circle the Earth and travel in smaller circles within that to explain their motion. Theories of epicycles are very popular among scholars because anyone could come up with a new one. Some theories had between 40 and 100 epicycles to explain the motion of the planets. But the truth is, as the great Indian astronomer Somayaji had said in the 15th century, it's more likely that the sun is the center of the solar system and Earth is one of the planets circling the sun. Now, in Galileo's time, there was another controversy about whether light had any speed at all. Many fine minds of the time, like Johannes Kepler, for instance, thought that there was no speed of light. It simply traveled instantaneously, everywhere at once. Now, Galileo suggested testing the speed of light by placing lanterns on distant hills to time light's passage. But Galileo didn't have a distant enough hill or a good enough clock. Galileo could only conclude that if light had a speed, it was too fast for him to measure. Now, the first evidence of light speed came from one of Galileo's discoveries, the moons of Jupiter. By the 1670s, there was an anomaly in observations of Jupiter's innermost moon, Io. Astronomers would try to predict when Io would appear from behind Jupiter, but sometimes it would show up late. A young astronomer named Ole Romer, working in the Paris Observatory, realized that the delay was due to the time it took for Io's moonlight to cross the solar system and reach Earth. Roemer predicted that on a certain day in 1676, Io would appear from behind Jupiter precisely 10 minutes late. On that day, Ole Roemer's prediction was right on the money, but at the time, few believed him. The Paris Observatory's director, Domenico Cassini, was a fine astronomer, but he refused to believe there was any speed of light. It would complicate all his calculations. It was 50 years until the 18th century before other experiments on Earth proved that Roemer was right about the speed of light. Now today, the speed of light is part of our science. It's been measured at 299,782 kilometers per second. Now, why it's that speed? Why not slower? Why not faster? Why isn't light infinite? That's been a mystery. Now, I've been working on a cosmology which can be described by a simple equation where the universe has a scale r equal to c times t, where c is the speed of light and t is the universe's age, about 13.8 billion years. Now, we have many observations indicating that the universe expands. This actually predicts that the universe expands because as t, the age, gets bigger, r expands. Now, the universe can't expand at the same rate forever because gravity would slow it down. So I'm going to skip a lot of mathematics, and this leads to a very simple equation, something that can fit on a t-shirt. Gm equals Tc cubed, where G is the gravitational constant, M and T are mass and age of the universe, and C is the speed of light. This actually predicts that when T was tiny, C was enormous, and the universe expanded like a big bang. As time T increased, the speed of light slowed and is still slowing today at a very tiny rate. This predicts that in a year, the speed of light would change by less than 1 centimeter per second. It's a very tiny change, but this would actually solve many problems with cosmology. For one, the cosmic microwave background. We've all seen pictures of it. The temperature of the sky is the same within 1 part in 10,000, as if different parts of the...
Ma'am, sorry for the disturbance.
Oh, pardon me? Oh, as if different parts of the universe could have been in contact with each other. Can you still hear me?
Yes, ma'am. We can't see your screen share, ma'am.
Oh, you can't see the screen share?
Yeah, we can't.
Well, I can see it I can just stand by, I can see it on this end. Just a moment.
Ma'am, you used any presentation?
Yes, I've loaded the presentation in there.
But we can't see that, ma'am.
Let me see. Well, I'm going to try a few buttons here. I'm going to try the button at the bottom of the screen.
Yes, ma'am. You can see the screen microphone option, start
Yeah.
stop camera option, screen share your screen option.
Let's see, that didn't do it. I'm going to try this one. Nope, still not doing it.
Share your screen option. Your entire screen share. Click the screen.
Okay, I'm clicking the screen.
Like this. Now you can see my screen. We can see only your face.
Okay. Yes, I've tried the screen share. Yes, I pressed the screen share button. Seemed to be working.
Okay, ma'am, no problem.
I,
You can continue
I
your
can
session.
I can continue this without slides.
Yeah, yes, ma'am. Thank you, ma'am.
Okay. Anyway, a changing speed of light would solve many problems with cosmology, such as why the microwave background radiation seems to be the same temperature. Now, this is the problem that an idea called inflation was invented to explain. Now, there have been many people who have tried to find evidence of inflation, but it's not testable. But if the speed of light were faster in the early universe, it would explain all the things that inflation does without any imaginary inflated particles. It would also explain a problem of Earth's climate. According to theories of the sun, life should not have evolved on Earth at all, because the early sun was only 75% as bright, and Earth would have been frozen solid. But that can't be true, because we have evidence of life nearly 3 to 4 billion years ago. I worked with the scientists at NASA who found clues to fossil life on a Martian meteorite 3.5 billion years old. Clearly, something was making both Earth and Mars warm enough for water and life several billion years ago. Well, the sun turns its fuel to energy according to E equals mc squared. If the speed of light were exactly as much faster as the math predicts, then the sun's temperature several billion years ago would have been almost exactly what it was today, and life could have thrived. In other words, if the speed of light had not changed, we would not be around to talk about it. Finally, a changing speed of light would solve what's considered the most profound problem in science, the so-called acceleration of the universe. Now, we know the universe is expanding because the greater an object's distance, the more its light is shifted into the red. When physicists observed distant exploding stars, type 1a supernovae, they found that their redshifts were increasing in a non-linear fashion, as if those supernovae were accelerating away from us. Since an accelerating universe would violate many physical laws, like the first law of thermodynamics, the conservation of energy, they had to hypothesize a repulsive energy, a dark energy, which would cause the universe to accelerate. Dark energy theories are very popular because almost anyone can think of one. But it turns out that the dark energy idea was all wrong. A study released by Korean astronomers a year ago, January 2020, showed that dark energy does not exist. Another paper released in October 2019 also showed there's no such thing as dark energy. And just this week, a new study verified that dark energy does not exist. However, if the speed of light had changed since the early universe, it would make distant supernovae appear to accelerate, exactly as the data shows. So supernova data doesn't show the universe accelerating, but it does indicate the speed of light slowing. Now, of course, I read fashion magazines too, and it's been fashionable to say that the universe is filled with dark energy. But there are other ways of testing the speed of light. Now, Galileo suggested testing it with lanterns on distant hilltops, but didn't have a distant enough hill. We've had a distant hill since July 20th, 1969. On that day, Apollo astronauts planted a lunar laser ranging experiment, which is a reflecting mirror on the moon's surface, which allows astronomers with lasers on Earth to measure the moon's distance to the centimeter. Now, all things change with time. We've known for a long time that the moon's distance is increasing due to tidal forces between Earth and the moon. Now, the lunar laser ranging experiment has measured that at only 3.82 centimeters per year, but that's too fast. If the moon were gaining momentum at that rate today, it would have been in the same place as Earth barely 1 billion years ago. And geological evidence from moon rocks, which I've been able to examine shows conclusively that the moon is nearly as old as the solar system, over 4 billion years. Now, other experiments disagree as to how fast the moon is receding. I'll go over them quickly. One of them used fossilized sediments called tidal rhythmites. These are fossils left behind when the tide leaves layers of sediment on a beach. Now, examination of those sediments and measuring them can show us the distance to the moon and therefore the length of the month many millions of years ago. And the sediments show that the moon's only receding by barely 2.9 centimeters per year, 1/4 less. Another experiment has used eclipse records. Astronomers in India have been reporting eclipses for centuries. When an astronomer in the year 136 BC recorded the narrow track of an eclipse passing over a city, it provides a precise measure of how Earth and Moon's relationship has changed. Now, a study of over 2,000 years of eclipses have shown the moon is only receding 2.91 centimeters per year. A third experiment uses computer simulation to simulate the interaction between the Earth and the moon. And it also agrees, only 2.9 centimeters per year. So 3 entirely independent experiments agree the moon is receding much slower, 2.9 centimeters per year. But the Lunar Laser Ranging Experiment disagrees by over 12 standard deviations. Physicists often look for a 3 or 4 sigma result. This is a 12 sigma result. Why? Well, if the speed of laser light were slowing, the time for light to return from the moon would appear to increase each year, making the moon appear to recede faster. Now, the math predicts an anomaly of 0.92 centimeters per year, exactly matching the 12 sigma anomaly. This is one of the most accurate scientific predictions of our time. The chances of it being wrong are 1 in many millions. So a final experiment I'll tell you about is going to be conducted on our space station. The other way to complete Galileo's experiment is to build a better clock. ACES, the Atomic Clock Ensemble in Space, is due to be launched to the space station within a year. The purpose of this experiment is very simple: build a better clock. In orbit, an atomic clock can be more accurate than any clock on Earth because Earth's gravity will not interfere with the vibration of atoms. ACES is due to launch within a year. One of its principal scientific goals is to search for anisotropies, or changes in the speed of light. Will ACES verify a change in the speed of light? Time will tell. But we have every reason to believe that there may be a sea change coming in the speed of light. Now, I'm going to take this a little bit further and tell you about something that's going to affect you even more. Now, I described two equations, very simple ones. I could restate them here. R equals C times T, where GM equals TC cubed. Now, in the natural units pioneered by Max Planck, those two equations can be combined into an even simpler expression, which you could write down M equals R equals T, where M is the mass of the universe, R is its scale, T is its age. This has got to be the simplest equation of all time, but until recently, no one could explain what it meant. What this means is that the tiny Planck units, the smallest units in nature, are fundamental. In other words, time does not increase continuously, but in stages, like the ticks of a clock. Space itself is not continuous, but has a granular structure. And as for the Planck mass, well, that's what the rest of this talk's going to be about. Now, the Planck mass is about 2.2 times 10 to the negative 8 kilograms. It's something you can see. It's about the mass of a flea's egg, or one of my eyelash hairs. Now, many things in nature are smaller than the Planck mass. The proton mass, 1.6 times 10 to the negative 19 kilograms, is many orders of magnitude smaller. Now we can measure small masses with a mass spectrometer, but those instruments measure inertial, not gravitational mass. Now, inertial mass is experienced when an object has resistance to a force, which is why even in microgravity, an astronaut has to push to move a heavy object. Now, gravitational mass, according to general relativity, causes curvature of space-time, which affects other objects and even the propagation of light. Now, as Galileo showed on the Leaning Tower, when you drop two small objects from the tower, they travel towards Earth at the same rate because of Earth's gravitational mass. In 1971, the Apollo 15 astronaut David Scott repeated Galileo's experiment on the airless surface of the moon. Now, the equivalence principle of general relativity assumes, and I say assumes, that inertial and gravitational mass are always the same, but that has never been tested for small masses. These equations predict that the Planck mass, 10 to the negative 8 kilograms, is fundamental. In other words, two tiny particles fall towards the Earth because Earth is big, but they do not attract each other. Now here's another visual aid for you. This is a simple experiment that any of you could do in your classroom or in your laboratory. As you can see, this is a vacuum chamber where the air has been pumped out to simulate the vacuum of space. Within this chamber, we place two tiny masses, barely the size of a period at the end of a sentence. I prefer to use spherical grains of limestone, which are called oolites, because they naturally form spheres. I select two oolites of a radius of about 0.2 millimeters. They will have a mass of about 1 times 10 to the negative 8 kilograms, slightly less than a Planck mass. I place them within the vacuum chamber, remove the air. They're placed upon a frictionless surface. They are grounded to the surface to remove any electrostatic attraction, and they are observed. Now, according to the laws of gravity, those two little grains should attract each other gravitationally, but after many trials, no movement is detected between them. This indicates that their mass is quantized, and these tiny masses do not attract each other. This is something you observe, every time you dust off a shelf. The dust particles fall towards the Earth, but they do not attract each other. The phenomenon of dust bunnies gathering in corners is actually caused by aerodynamics and electrostatic forces. Now this has many, many applications. And I'll just describe just one of them, the size of the cells in your body. Now all large life forms are made up of cells of less than the Planck mass. The largest cell in the human body is, within our female body, the egg cell, the ovum, which grows to a mass of just under the Planck mass. Now, when our egg cell is fertilized by one of your male sperm cells, the ovum cannot grow to larger than the Planck mass. It must divide to create more cells. In the process of mitosis, the nucleus breaks up into small strands that move to opposite ends of the cell to begin the process of dividing. Now, these processes exist because gravity is quantized. If the cell were bigger than the Planck mass, self-gravity would affect its internal processes. So that is why your bodies are made up of cells of less than the Planck mass. It's related to cosmology. Now, we have had two theories in the past century. one of quantum mechanics and one of relativity. What this math shows that there are not two theories. They are part of one big theory, that gravity itself is quantized. Now, our understanding of quantum mechanics has led to all the things you use in your classroom, to lasers, to transistors, to computers. Now, if we could understand the quantum nature of gravity, which can be shown in this simple experiment, we would be on the way to someday understanding, eventually opposing, and possibly even controlling gravity. And that would make any aircraft we work on today hopelessly obsolete. We would no longer need to use rockets or wings to keep things in the air because we could oppose or manipulate gravity. And this is another experiment which we hope to test in cislunar space soon. You could reproduce it yourself. The small version of the experiment looks like this. Stand by. Well, oh, we don't have that slide, but it's an object that looks like a marble, about 1.8 centimeters in diameter, designed to be carried into space and observed. In the microgravity of a space station or a spacecraft, we can isolate the experiment from all the effects of Earth's gravity and show conclusively that gravity is quantized. And this is an experiment I hope to see in space within the next 2 to 3 years. So I've talked for my 30 minutes. I want to leave a little bit of time in case you have any other questions or anything else you'd like me to talk about. But this is an extraordinary time to be in science and engineering. I mean, India and other nations have launched spacecraft to the moon. I hope to be involved in one experiment to place a telescope on an unmanned probe, and hopefully within several years to send people around the moon. And in our theoretical science, we're on the verge of solving the problems of inflation, of so-called dark energy, truly understanding the origins of the universe, something that affects even the size of the cells in our bodies. And I know this seems like a very dark time, but this is a time of light. Many things change. We may soon change, truly see a big change, a sea change in science. And I would like to leave the rest of this time open for questions, and thank you for your patience.
Ma'am, I have one doubt. Ma'am, I have one doubt, ma'am. Light don't has any masses, but how is affected in gravitational lensing?
Oh, actually, they're related. Gravitational lensing is caused by a large mass causing the path of light to bend. Now, we've known for a long time that gravity causes light rays to bend. I've extended the mathematics to show that gravity also causes the speed of light to slow, which is something that Einstein explored back in the year 1911, but couldn't quite complete. So not only does gravity cause light rays to bend, gravity affects the very speed of light. So gravitational lensing is just one start. Gravity also affects the speed of light.
Thank you, ma'am. Any other students have any doubts? I think anyone don't have doubts, ma'am. Thank you, Mr. Luis Riofrio. That is wonderful session for sharing your knowledge and thoughts, ma'am.
Oh,
Can we
thank
end
you.
the session?
Right. Okay, thank you. I hope you enjoyed it.
Yeah, yes, ma'am. It's nice. Can we end the session, ma'am?
Oh, yes, we can end it.
Thank you, ma'am. Thank you very much.
Thank you for your time too.